I'm Matt Godbolt.
And I'm Ben Rady.
And this is Two's Complement, a programming podcast. Hey Ben.
Hey Matt.
What are we going to talk about today?
I think we're going to talk about compression today.
So, like squishing things?
Yeah, squishing bits.
Oh, bits?
Taking bits and squishing them.
So
which,
like,
you know,
if you squash a 0 like flat, it becomes a 1.
Yeah, right.
That kind of thing. I see. That's one
Unless
way
you
of doing
squish it down, in which case it becomes an underscore.
Oh, or a minus.
Well, if you got to squish it from both sides to make a minus.
That's true.
These are the compression algorithms that
These
we
are
need
the
to talk
compression
about.
algorithms that we're here to talk about today. Which one of those is zlib? Well, in the true spirit of these podcasts, we haven't really thought too much about what we're going to talk about. We did discuss that we should talk about compression. Mm-hmm. A number of months ago, I did a presentation at work about the various different compression algorithms, or rather the way that I was subverting them for a sort of side project I've got called, I can't even remember, Z-index or Z-index or Zindex, which is a way of archiving and searching through archives that you've previously have made, gzipped files, and sort of random accessing within them, which is something you're not supposed to be able to do, but with a little bit of sidebound data you can. But that meant trying to understand or explain to people how zlib worked, which meant talking about compression. And then we were like, hey, we should talk about that. So here we are.
Yeah.
What do you want to talk
about that?
I mean, like, what even are a compression?
So yeah, aside from turning, zeros into other various characters on your keyboard,
which is not really what they do, just to be clear. It's not a real thing.
Yeah, I mean, quite often it makes sense to trade a little bit of extra CPU time in order to get a little bit less storage space, or basically just bytes, because you're transferring something over a network or whatever it might be.
Right.
Lots of other contexts. And so you want to take a bunch of data and shrink it down into something smaller. And there are many algorithms for this, and we're going to talk about them today. But I think the first thing we should talk about are sort of the different trade-offs, because it's like, well, why wouldn't I want to make my data smaller? And how do I want to make my data smaller? And other considerations that you might have when choosing one of these algorithms.
I mean, so obviously the first thing that springs to mind is, how good is the compression algorithm at squishing my data in the first place? Like, given a input file, how much smaller can it be after it's been compressed? And that's really easy and objective to measure. You take your 100K file and you apply your compressor to it, and you're like, go, hey, it's 200 bytes now. That's awesome. Fantastic. Mm-hmm. And this one makes it 190 bytes. And you're like, that's obviously better. Let's just use the 190 byte one, right? So that's the first thing, is the compression ratio.
Yeah, and people do tend to talk about it as a ratio, right? Or sometimes a percentage, right? You'll get 90% compression, which the way I interpret 90% compression is you took something that it's a little, I feel like it's a little weird when you say that, because it's like, I took 100 bytes and I compressed it down to 10 bytes.
Right. I saved 90% of the original size.
I saved 90% of the original, right?
Yeah.
Which, it's like, so I got 10% was the result, but it's like 1 minus that, right?
Yeah.
And then, you can have, ratios. I feel like you'll also see things where people talk about negative compression ratios in order to express something that actually got bigger when you compressed it, which can also happen.
Oh, yeah,
but that sort of breaks that model too, right? So I think it's really important when you're talking about, and this is true all the time when you're talking about percentages and ratios and things like that, where it's like, it's kind of easy to lose track of what the numerator and the denominator were. So I feel like when you're discussing these things, it never hurts to sort of be explicit.
Right. So when we're talking about compression ratios, well, I don't know that we'll have any concrete things, but then in that specification, 90% would mean it is 90% smaller, means that 90% of the original size went away, and you're left with a file that is 10% of the original. Right. That makes sense. So obviously, naively, you want to pick the thing that compresses your input to be the smallest output, right?
Right.
But there are other trade-offs, obviously.
Right.
Otherwise, we wouldn't be bringing them up. We'd be like, well, we're done. You pick the smaller one.
Right.
So what else? What else is important?
Well, there's compression, how long it takes to do the compression.
Right.
And there's also how long it takes to decompress it.
Right.
And for certain algorithms, there's how lossy it is, if it is lossy.
Right. That's a good point.
Mm-hmm.
I suppose, the idea that we could talk about loss E compression as well might be too much for one podcast. So maybe we'll table that for another time. But yeah, so I was thinking we would talk really about lossless compression in this chat, because the world is going to be. Maybe we'll get to it at the end. Who knows? Again, exposing the listener to the lack of planning that goes into this. In fact, is a watchword of this podcast.
Yeah. I mean, at least asking the question is always a good one, right?
Yeah.
Like, is this actually lossless compression? Because not every compression algorithm is.
Can I assume that when I decompress it, I get the exact same bytes that I put into the compressor? That seems is kind of the definition of lossless. Versus image compression and stuff, which actually loses some of the data and you don't get it quite back, as we've all seen.
Audio, video can all be a little lossy. Yeah.
So obviously compression time and decompression time. Another thing that I think is an interesting one to consider is how much code it takes to decompress your input, because kind of an implied input to your decompression data is the thing that can decompress it. Now, obviously, in on a Unix system or whatever, you've got gunzip, and it's like, okay, there's 500 bytes of 500k of executable somewhere. You don't have to worry about it because everybody has gunzip somewhere, and so you can kind of like, oh, all right, we can decompress this. But like, if you are working on an embedded system which has got limited resources, which is one of the main reasons you might want to do compression. Like, hey, we've got an SSD and we need to read things off of the SSD and decompress them into RAM to run them or to do whatever. Then you realize that you actually have to budget for the decompression algorithm and the amount of code space that it takes up. And if you have like a compression algorithm which is like, hey, I have a lookup table and the lookup table is 200 megabytes of like canned values, then and you just store in your compressed version, you're like, well, it's just number 7 in that table. That's great compression, but you need a very big decompression table somewhere else.
Right. Yeah, that's a great consideration, actually.
I mean, it's top of mind just because of like looking at compression on like old 8-bit machines that I'm looking at, like, oh, this is cool. Look how much you can compress, but unfortunately the decoder is like 5K, and that's too big.
Yeah. And I mean, I guess part and parcel to that is kind of like fonts also have this property. Is like there's a certain percentage of these things are going to be available in any environment that you're delivering the data to, because again, a lot of times when you're compressing stuff, it's in order to send it somewhere, and the question is, can the person on the other side actually uncompress it, right? And so depending on the exact transport mechanism and the clients involved and a bunch of other factors, you may or may not have access to those algorithms. And thinking about which ones are going to be more ubiquitous and which ones are going to be like, oh, actually, we need to first send the decompression library and then we can send the data
the actual
itself.
Data, right?
Yeah, is a sort of another dimension of that in a way.
And I mean, if we talk about ubiquitous, I mean, the most ubiquitous compression algorithm that I'm aware of would be deflate, which is the algorithm that powers zip files and GZ and every web transaction you've ever done, although I guess Z standard has now taken it over. But yeah, all right. Most web transactions are compressed with deflate, and colloquially everyone sort of refers to it as either zlib, which is the library that implements it, or just gzip, even though it really is the same algorithm inside your Windows zip files as well. And that uses a number of techniques under the hood, and we can talk about what those techniques are. But like, I guess let's talk about what types of things you can do in a compression algorithm.
Okay, yeah.
So one of the things that I used to do a million years ago on 8-bit machines was you would observe that very often you'd have sequences of bytes that repeat. So you've got usually like a picture, an image, or a sprite in this instance. You'd be like, well, okay, it's the value 0, 80 times, followed by a 1 and a 7 and another 3 zeros and then another 100 zeros and then whatever. That doesn't make sense, but whatever. So even just eyeballing in a hex editor, you can see that most of it is zeros. And so one might just go, a simple compression algorithm would be, okay, if I see a 0, count how many more zeros there are, and then when the compressed output is 0 followed by how many zeros there were. And that's great if 0 is the only thing you want to do compression for, and this is like run length encoding, as this is RLE, where we're saying, hey, I'm going to look at how long the run of this particular single number is, and I'm just going to repeat it. Now, that's cool. It makes sense. The decoder is easy. You read bytes, and you just copy them. But every time you see a 0, you read the next byte, and you write out that many zeros. Straightforward. Right, and it's pretty effective, and obviously you can imagine that the decoder is trivial. The encoder is pretty trivial as well. But the first and obvious thing you might notice is, well, what if there's only 1 0?
Right.
Now you're sending 0 followed by a 1.
Right. So
and that's twice as big as it was when it came out, which is not a good look. And that goes to your original point about like having a negative compression ratio. And this is one of the reasons that you can get negative compression ratios is that sometimes you try to encode some clever things and they're not as clever for the particular stream of data that you've got. And that's a problem.
Yep.
One way around this is to divide the world into little blocks and say, let's compress every 512 bytes, let's say. And then you say, immediately before every block, I'm going to put a flag that says, did I apply run length encoding or did I not apply run length encoding or some other compression, whatever algorithm. And then you can try to RLE compress 512 bytes. And if it gets bigger than 512 bytes, you go, let's just store it as is. And then you just put the flag that says, this is just exactly as, it's just byte for byte, copy the next 512 bytes. And of course, you can generalize that. But, in the worst case now, what we have is every 512 bytes, we add 1 byte that says this isn't compressed. And now we still made it bigger, but hopefully not as bad as it would be if every byte was there. And that's another reason. So the sort of metadata about the data that explains how the compressor is configured or how to decompress the next bit can take up more space than if it was just raw data. So that's run length encoding. That's one of the easier ones. What else could we do to compress data?
Well, that's a good question. I don't have an answer to that.
Well, what is the most common letter in the English language?
E.
R-E. No, E. Yes, the E. Right. So, how many bytes does it take to store an E?
Well, normally it's 1 byte.
1 byte, right.
Yeah.
But we know that E is more common than if we're compressing, let's say, text. E is more common than almost every other letter. Well, it is the most common letter, sorry. So what if we could say, let's forget about bytes. Let's just treat this as a stream of bits. What if I said I could encode an E with only 2 bits? Like maybe let's just say 0 and then 1 is an E. As in the binary 0, 1. And then every other letter, for the sake of ease over the air and not without a whiteboard to draw anything on, everything else is going to be a 1 bit followed by 8 bits of the rest of the letter. So that means that every other letter is now 9 bits, boo-hoo, but every E is only 2 bits.
Right.
So this is a kind of like, think of it like the RLE in terms of we're trading off something to encode something which is hopefully more common or is more compressed, but we've made it slightly more pessimistic in another case. But now, if you imagine like a third of all of your text is an E, you've dropped that third down to 2 bits and everything else is 9 bits. Now, I can't do the maths in my head. It's terrible to do, but there is a way to construct a optimal tree of bits, 1s and 0s, that give each character that you could possibly have inside your output a variable number of bits based on how common it is or not. So while an E may be 1 0, I can't remember what I just said, 0, 1, whatever. And now maybe the next most common letter is, I don't know, T. That might be 1, 0, 1. And that's unambiguously a prefix that only means it's T. And it's 3 bits now. And then you can start building a tree with all of the other things in until you get to like, the Q and the Z take maybe even now 12 bits to unambiguously encode. But now, effectively, we are storing the letters with codes that are inversely proportional in length to how common they are. And now the document we're storing, provided it's an English document, and fits this sort of statistical arrangement of probabilities of how likely each letter is, now we can store it in considerably less bits. I mean, it may make sense, like there's a reason why the phone number for emergency services is just 112 or 999 or
911.
What is it? Whatever. Oh, yeah, that's what it is.
You
What's
should
the number?
probably know what that is if you live in the United States. Just saying. I would recommend that you write that down.
Okay, I'm gonna write that down. It's like So I was gonna say that like phone numbers have like this sort of like feeling of like they're unambiguous. 911 doesn't code. That's not the beginning of someone else's number. You never accidentally code it, but that means that anyone else starts with like a 0 or a 1 or something like that, which is a reason why. So you were going to say something.
Oh, I was just going to say, so one of the things that I've heard about frequently when talking about different compression algorithms is using a dictionary as a compression mechanism. And one of the things that I've heard about that is that you do, and I don't know if this is universally true, but it's something at least that I've considered in the past, is you either need to do this thing where you're saying like, okay, well, let's assume that we're going to be compressing English words. Like, okay, that's a big assumption, but sure, for certain applications that makes sense. In that case, you can kind of define some of these things up front, including something like a dictionary, right? So you can make just a dictionary of words, right? And you can have each byte sequence refer to whole words instead of individual letters, and that would be another way potentially to do this. And there's like somewhere in the order of tens of thousands of words in the English language, so your dictionary wouldn't be all that big, and maybe you'd get good compression out of that. Alternatively, you could build the dictionary after you've run through the data and found the most frequently occurring patterns or words or sequences of bytes or whatever you might find. But the disadvantage of that is that now you sort of have to run through everything before you can build that dictionary, or you need to have an algorithm that will build it on the fly or something like that. And so that seems like a whole category of things where you're sort of trading off between either knowing what kind of data you're processing beforehand or doing some things post hoc after you've run through the data that might make it a little bit more difficult to work with if you were, for example, trying to do compression as like a stream. Like you don't ever want to have to seek through the data multiple times or use a whole bunch of memory while you're compressing it. And so you have these trade-offs that you need to make when you're doing that. Are there compression algorithms that you've worked with before that sort of make these trade-offs in different ways?
Well, absolutely. So we're actually slowly walking towards what deflate is going to be, which is a cool thing, and totally unintentional, which is great. So just on that one thing you mentioned about like if it was English words and the probabilities and the thing as I described, obviously if you knew the compressor and the decompressor both knew it was English words and they'd previously agreed on the frequency of letters. I'm talking about the letters thing first. They've previously agreed on the frequency of letters, then they would both already know that E is 01 and P is whatever 1001 or whatever like that. But if they don't know that, or if you want to, like as you say, have a sort of dynamic idea about, well, I ran through the data and I counted how many of each letter there were, and now I'm going to build my tree of like how many bits code for which letter uniquely for every piece of data, then you need to actually transmit that tree to the other end so that the other end can say, okay, we agree on the code book of like how many bits mean which letter. So that's a downside with dynamically sending that information across, because the tree is not free. It takes up some space, right? So so you have to offset the compression you get from the tree with the fact that you have to send the tree at all. One of the cooler tricks is, like exactly as you said, is what if you, instead of treated each byte individually, you also said, well, dictionary elements themselves are just other symbols. So now we're just, instead of compressing character at a time, byte at a time, we'll just call them symbols. And let's say the first 255 symbols are the literal values 0 to 255 of the byte 0 to 255.
Okay.
And then let's say symbol 256 is the first of my dictionary. And it just means the letter, I don't know, the word cat, right? And the 257 means dog and whatever, right? And you, again, if you could previously agree this on both sides, the tree building step that we talked about, where depending on the relative probability or a number of occurrences of each of the symbols that you see, doesn't care how many bits long those symbols are, right? You can have 1 billion symbols in that tree if you wanted. And it will still be the case that the most commonly occurring ones will have the shortest bit encoding, and the least frequently occurring ones will have the longest one. And obviously, as you put more and more things in the limiting case, that can be a very, very long prefix, so to the point where you're like, well, this is longer than the word that it's coding for in the dictionary. Let's not bother with this anymore. We might as well just encode it using smaller words. So a way of naturally extending the table of characters and their prefixes is just to throw in words as well, or previously agreed dictionary components, so that, you know, hey, this pattern appears in my data more often than not. So when you see 1011, that actually means the entire string cats are cool, right? Because that happens in my application a lot, right? That's the kind of thing you could do. And but there's another sort of aspect, which is now I have to either transmit that dictionary, boom,
right. Yes.
Or we have to previously agree on it again, and now we're back into the world of like, oh my golly, how big is this dictionary? And my little embedded system is now scuppered, going, oh, I need to store, you know, a 50 megabyte table of this dictionary that we've agreed upon, and all the prefixes to go with it. So that's a shame.
Right. And if you do transmit it, you have to transmit it after you've examined the data.
Correct.
Right? Which means if you're, and maybe I'm wrong about this, but if you're decompressing on the other side, you can't really decompress then in a stream, because you don't get the dictionary until the very end.
Well, usually in this instance, you'd have to get the dictionary up ahead because the compressor needs the dictionary as well, if you were to do it that way, right? Because as you're going through, I'm assuming that you have a static tree that you've built that is like, here are all the probabilities, and they therefore don't change. But obviously we can talk about how you can actually update them. And that sort of leads us naturally to the next thing, which is, what if you didn't transmit the dictionary at all?
Okay.
Because if I've just transmitted the letters C, A, and T, because that's the first 3 letters of the document that I'm sending, I have actually also just transmitted the word cat, right? It took 3 bytes, or it took however many the relative probabilities of the C, the A, and the T were to transmit it. But now I effectively have a dictionary record for the word cat. It is 3 bytes back from where we're currently decompressing. If you've just if you're the decompressor and you've just written out the C, the A, and the T because you've decoded them. So what if, instead of sending an explicit dictionary of things that I've previously agreed, the dictionary entries themselves are effectively references back from earlier in the document.
Interesting.
And so now, anytime I want to say the word cat, I can say, depending on where you are in the output, go back however many bytes to get to the C and copy 3 bytes, C and A and a T. And so now I've effectively got a dynamic dictionary that allows me to refer back to anything I've previously transmitted. And so suddenly, if I've transmitted the word cat, I can say cat over and over and over again with just one symbol. And that's pretty cool. Even cooler is, what if I had the letter A 700 times in a row? You remember in our original description, we were talking, well, you know, you have run length encoding. I could transmit something that says, hey, there's an A followed by there's a ton of them, all right? So, you know, just copy that A 600 and, there's 700 of these A's in a row. But if I say, transmit the code, here is an A, so the decompressor has written out an A, and now I say, hey, there's a dictionary element I would like you to use. It is, go back 1 character and copy 699 times.
Yeah, okay.
So what I've just done is if you can visualize it, I'm reading the A immediately that I've just decompressed, and I'm copying it to the current location, and then the 2 pointers are going to walk along, and so that A is going to get smeared out 700 times. And so this dictionary compression that we've just talked about, where I can back reference to a previous part of the document, gives us RLE for free. That is run length encoding. I can just take an A, and then I transmit the dictionary entry that says, go back one, copy 600, and I've got my run length encoding.
So the size of that amount of data that refers to how far back in the stream you go, right? Whether it's 4 bytes, 8 bytes, 16 bytes, however big it is. Am I correct in assuming that that is the amount of previous data that you need to hold in memory in order to decompress the data as you stream through it?
Exactly right. This is referred to as a sliding window because it's the last M bytes, usually something like 64K, that you, even if you're a streaming decompressor and you're passing the bytes onto some other thing, you're printing them directly to the screen, whatever you're doing, because of this, you still have to hang on to the 64K of prior data in RAM so that when the next byte comes from the wire that says, hey, copy back 32K and it's 27 bytes from there, you need to be able to get access to that still. So obviously it does, and I guess this is something we didn't talk about, like the runtime memory requirements of the decompressor, right? You have to keep something around in order to be able to decompress. Yeah,
that is another consideration that we forgot to consider.
We forgot, an unconsidered consideration.
Right. Yeah.
So anyway, what we've got so far is we have a tree that lets us encode symbols, and symbols are not just bytes; they could be dictionary elements. And some of those dictionary elements are actually now phrased as go back n and copy m bytes. Now, this is glossing over the actual specifics of deflate, which actually has different trees for different things or whatever. But let's just stick with this for the quote simplicity of trying to explain it to somebody who's walking their dog at the moment or is pottering around the house
on the train,
on the train. Yeah. Exactly. Yeah. So, you mentioned a number of times, having to do multiple passes and the dealing of streaming and things like that. Unfortunately, that is something that the compressor is forced to do. In order to be able to make these determinations, what it's likely, and although there are algorithms for online building of the trees and whatever, typically what happens is that the compressor chunks its input data into sort of reasonable sizes, and then the compressor normally tries a few different types of algorithms, exactly as I described right at the beginning with the RLE. Like it goes, hey, let's try doing it with just a static tree. Let's try it with a dynamic tree. Let's try it with back references. Let's just and each time it says, does this work out as being smaller? And it would pick the block that is the smallest of them all. And ultimately, there is a didn't compress type block, storing it only, which only has a couple of bits at the beginning that says, oh, sugar, I couldn't actually compress this. And then here's just the literal data. And so that is the hedge for like the uncompressibility. And it bounds the maximum size of the compressed thing to be, only a tiny percentage bigger than the input in the worst possible case. So having done this, it's now run through. It sort of encodes the dictionary-based compression. It's trying, and that is, for what it's worth, a very difficult problem, right? It has to kind of search through the space of like, should I go back 2 bytes and copy 1 byte, or should I go back further in the document and copy slightly more? Now, going further back, I might be able to get a longer match that, because maybe I've got cat and I've got CA, and I can build cat by going back 700 bytes and copying 3 bytes, or I've recently done a CA. I can go back a smaller distance to get just the C and A, copy those two, and then just output a T. And those are equivalent in the output stream, but the exact bit patterns of how to describe those two operations of going back a long way and copying 3 versus going back a short distance will change the overall output compression ratio, because maybe the nearer ones are used more often, and so they'll have a smaller coding in the tree, and that kind of stuff. So there isn't like a one true encoding, and that's essentially when you're gzipping something and you do gzip -9, you're tending to try really, really, really hard and go through all sorts of different combinations and try different encodings to see if it'll work out, as well as there are some internal acceleration structures that are sized accordingly when you do that. And it's why it takes longer in the compressor, because it's essentially searching through to find what might be the best encoding of the data.
Yeah, I didn't realize that when you're telling these algorithms to basically try harder, what they're doing is trying more internal algorithms, more approaches, I guess, is one
amongst other things.
That.
Yeah, I mean, so most of them end up having to do. If you imagine what it looks like, you're trying to find a prefix in some data you've already sent out. So you've got 64K of the stuff you've previously sent, and then you're looking at the next byte in the compressor, and you're saying, "Oh, what is the longest match in the 64K buffer I've got behind me?" And one way to do that is to just go back all 64K and look for but that's a hugely order n squared operation you're now doing. Right. And so most things do some kind of stuff where they hash a few bytes and go, well, I'll just keep a hash table of like the prefixes of ABC, and I look at my hash table and kind of go, oh, I've not seen ABC, or if I have, it was too far ago, never mind. And then, as I say, there's all these other sort of subtleties about like, well, maybe you want to prefer nearer matches than further matches, because you're more likely to say copy 3 bytes ago over and over and over again, rather than copy 64,922 bytes ago, which is a very unique encoding compared to nearby, right? So there's a whole bunch of trade-offs up there. But anyway, so you've done this a number of times, and then you're going to tell the decompressor, hey, I picked to use a dynamic tree, which I'm going to transmit to you in this block, and then obviously it's dictionary decompression after that. So the tree gets transmitted, and there's a pretty compact representation for the tree in terms of which bits map to which symbols, and then the decompressor has to generate that tree and then obviously look through and just copy from before. But those chunks we're talking about, these like 64K-ish blocks that the compressor has chosen to like look ahead and kind of make its determination, those are different from the sliding window of 64K, right? That's a separate. Okay, those are separate things there, right? So because the compressor could just choose to look at the whole file and say, actually, this is this technique that I'm about to do, this tree that I'm going to build is good for the whole file. Let's send you the whole file. But for pragmatic reasons of not having to go all the way to the end of the file and buffer it all in memory if you're a streaming thing, usually it's chunked into smaller pieces. Chunking into smaller pieces also has a nice side effect, because it means that you get a chance to give a different tree every 32K, 64K, whatever the algorithm decides, the compressor. And so if you have a text file that's in different languages, hey, the first half of this is in English and then it goes into Norwegian, maybe you need a different set of vowels more often, or whatever, diacritic marks and stuff like that. Or, more generally in your data file format you're compressing, there's likely to be a big header at the beginning which has some characteristic, and then a whole bunch of like other data in the middle, which is a different thing. So it gives it an opportunity to kind of reset and change the relative frequencies of all of the symbols that are occurring, depending on the data, which of course is another degree of freedom the compressor has. Hey, it could choose not to do that. It could do the whole thing. It could try. It could try doing 1K, then 2K, then 4K, then 8. It's got a lot of degrees of freedom there, which means that again, it can be difficult to write an optimal or a provably optimal compressor. And this is all deflate for what it's worth. This is all what deflate does. Deflate has dictionary base, which if people know what Lempel, Ziv, LZ77, I think recently one Ziv or Lempel, one of the two died recently. There was which was sad. But anyway, Lempel Ziv is like all this dictionary based thing where you have like these back references to n bytes ago, copy M, and there are 100 different ways of encoding it or choosing to do it. And there's all the different LZ77s and other numbers. I can't remember what the other one is now. No, it's gone. Then obviously the tree, the tree is called a Huffman tree, and it's a Huffman encoding tree. It's a way of building these unambiguous sequences of bit patterns that will encode a node in a tree, and the length of that sequence is provably the shortest unique sequence that will get you to that particular point in the tree based on its relative occurrence, how often it occurs. So that's pretty cool. And deflate is built of those two primitives. in various clever bit packing encoding and other bits and pieces. So the devil is in the detail with a lot of these things. But there are some really other left field ways of compressing data. I mean, you mentioned lossy.
Yeah, right.
So obviously you could decide to just, divide everything by 2 and then that immediately you've saved 1 bit for every output value, and then you just multiply it by 2 on the way out, and maybe some values, everything's even, but who cares, right? For some data that might work. So, but sort of more wacky, and I still really haven't got my head around how this works, and also I can't possibly begin to explain this. A, because I'm not very good at understanding myself, but B, because we probably need a picture. There exists a transformation to your data called the Burrows-Wheeler transform.
Okay.
It is a reversible transform. That is, I can apply the BWT to my data and I get a permutation of all the bytes of my data, and I can reverse it and get my original data back, right? This has not changed in any meaningful way the contents of the data. It's just rearranged it.
Okay.
But the side effect of the Burrows-Wheeler transform is that it is sort of sorted your data. Your data is more sorted, it's more ordered because of the transform than it was before.
Interesting.
Right? Yeah. It is interesting. You take a megabyte of data, you apply the BWT to it, and it's a permutation of it, and the data, if you looked at it, was more likely to be A, B, 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 C, 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 D, 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 E, E, A, A, and it might go back to A again. It's not, it's not just sorting it.
Yeah.
And again, there's a great Wikipedia article on the BWT, and it's got a picture, and you can see what it's doing. And the way of reversing it is more tricky than you might think, but it can be done, right?
Yeah.
So if you apply the BWT before you throw it into a compressor, what you've done is you've made it more compressible,
right?
Which is cool.
Yes,
and that's what. Which one is it? Tar dot not XZ. Because that's another one. One of the BZ2. The BZ extension BZ2 for like tar.bzt2 is Burrows-Wheeler. I think the B inside that of bzip. So it applies it before it runs it into the compressor. And actually, while we're talking about that, there's another general sort of technique for compression, which is to apply a domain-specific filter to your data before you throw it into a compressor. Mm-hmm. So, for example, you might know that there are certain sequences in, say, ARM assembly code, or ARM machine code, I should say, that are very common, but they are relative to they're absolute locations, right? They are absolute locations in the file, or relative. So no, they're relative. Sorry, let me get this straight. They are relative. So you can imagine there's a branch instruction, and it has a relative destination. Okay. And so, but if every branch, if every third branch is calling the same absolute destination, their encoding will be different, because relative to where that branch is, it's a different offset, right? Which means it's unique. But if you were to extract that out and say, okay, well, these are all going to the same location, I'm going to make them absolute.
Right, yeah. Then
now suddenly it's the same bits every time. Every time we see that branch or whatever, or something like that. I've just butchered it, obviously. So there are certain things where if you know ahead of time that you can make the data more compressible in a reversible way, BWT being like a more generalized way of doing it, that's another a technique. But obviously the decompressor has to know how to undo that too, and it has to know that process has happened. And very often those are incredibly application specific.
Yeah, interesting. So it's like you're intentionally introducing duplication in your data in a reversible way, because it makes the compressions algorithm's job much easier.
Right.
And, I've never actually done the experiment before of just taking a bunch of random text, sorting it, and then compressing it.
Right.
And compressing it and seeing what the difference is. That would be really interesting.
I mean, it's a measure, generally speaking, is the measure of how much disorder in the file is the entropy, and, that gives you some kind of lower bound on how much you can compress a file. So obviously if you took a completely random file, if you catted dev random and you compressed it, you would imagine it shouldn't compress at all. It should be slightly bigger. But obviously, if you sorted it, what you're likely to have is an equal number of zeros, ones, twos, threes, fours, five, six, all the way up to 255.
It would compress really well.
And you'd imagine it would compress down to almost nothing, because it'd be like, there's 250 million zeros, there's 250 million ones, there's 250, and so on. And you're like, all right. So in the limiting case, you can get a really good ratio, but obviously it's not reversible.
Right.
But if you can come up with a way of encoding how to put the zeros back in the right place in the final document, then you're sort of edging towards a compression algorithm. But the amount of data it would take to encode the positions of all the zeros, for example, and then all the positions of the ones, should be the same amount of data as you put in the first place. So, there's no free lunch there, but it might be better to encode, or it might be easier to encode, which is like essentially what the BWT is doing.
Yeah.
And I'm sure I've butchered some description of it there, and we'll get people tweeting at us or mastodoning at us for those things. But one thing I did want to say, actually, just while I'm here, and because I've got the page open in the background now, I've been thinking about it, is that sometimes the trade-off you want to make in the compressor is, like imagine you're Google, and you want to send out the Google, there's a single Google.png or Google. Whatever.
Right.
And like literally every third web transfer will be of this in the whole world is of Google.png, right? So every byte you can save on that damn PNG is worth its weight in gold, right? I don't know how much a byte weighs, but whatever.
Yes.
Given that PNG internally is using deflate, which is another thing, it might be worth saying, I don't care about if it takes me 6 days to compress this PNG. If it saves me 1 byte, that'll pay for itself over the course of probably a day.
Millions and millions and millions of page loads, yeah.
Exactly. And so there are some compression libraries that are dedicated to generating almost perfect bit streams of this is the smallest conceivable sequence of valid deflate bits that will cause the output to be what you want it to be. And one of those is something called Zopfli, Zopfli. It hasn't been touched in years. But it is a way of creating and compressing a source document and generating essentially the optimal output. And it takes hours.
Interesting.
A really long time. And it's very limited. You can't do very much with it. The only reason I know about it is because of hobby projects that use this to compress stuff on a PC to be then put onto an 8-bit computer, where again that trade-off's fine. The source data is small, it's 20K, but you want to compress it as much as actually possible for your 8K demo you're trying to get working, or your 4K demo you're trying to get working on your 6502 based machine. And so it's worth saying, well, I'll spend 30 minutes in my build squishing it those 2 more bytes because I can do something cool with it. Or again,
worth it. That's neat.
And I think the way that they work is actually they start backwards. They start at the end of the file and work backwards, and they try and find the optimal thing that would encode what remains. Something like that. Somebody explained it to me once over a pint, and it made perfect sense at the time. And like so many of those things, as I say it out loud now, I'm like, how could that work?
How did that work? Yeah, exactly. Well, I think you were definitely right about not being able to get to things like lossy compression in this episode, because it seems like this is a very deep topic, which maybe warrants some follow-ups.
Right. So I'm going to just do honorable mentions now. We've talked about deflate all the way through. Google and Facebook have both got their own versions of, again, I think they're all using the same techniques and slicing and dicing. There's the same tricks, but with different trade-offs. But Z Standard, which is now seemingly the most de facto compression, at least in our company, Z Standard is coming, and Snappy. They're both libraries again that are not deflate, but they use broadly the same parts. But yeah, honorable mentions for those only because we've talked about gzip, which is ancient, really.
Right. Right.
And they those things, the Snappy and Z Standard, are usually faster and have comparable, if not slightly better, compression ratios too. So. And one last thing, there somebody posted a so we talked about PNG just then, which is very complicated file format, and ultimately the internals of it are in fact deflate compressed and whatever. Some random coder just came up with their own image file format using a relatively made up off the fly, like, well, 1 bit, and then it's like, this is how we encode the next pixel, 2 bits, and this is how we encode the next pixel, whatever. And it beats PNG hands down for lossless. So there is still room in the world for compression formats that are incredibly bespoke. So this is just for image data, but
still, though, there's a lot of image data in the world. That's
exactly. I wish I could remember it. And again, I'm sure we'll put something in the notes that says what it really is.
Right.
But
exactly.
yeah, as you can tell, I love this stuff. If I remember rightly, I've got like an online view where you can type in words and see how the a dictionary compressor would see it and how a Huffman tree would see it.
Well, we're definitely going to have to put that.
We'll
in the
link
notes.
that in the notes too, so that you can have a little play around and kind of give a more of a visceral understanding about what's going on behind this. But it's fun.
Yeah, that's really cool. Really cool. All right. Maybe part 1 of 2. I don't know.
Maybe. Who knows?
Make that.
We'll
see. We'll see if it
how
works
it
out
goes.
like that. All right, man. Well, I'll talk to you later.
Until next time, my friend. You've been listening to Two's Complement, a programming podcast by Ben Rady and Matt Godbolt. Find the show transcript and notes at www.twoscomplement.org. Contact us on Mastodon. We are at twoscomplement@hachyderm.io. Our theme music is by Inverse Phase. Find out more at inversephase.com.